Hi everyone. In this talk, I will talk about polynomial bounds on parallel repetition for all three-player games over binary inputs. The title is long, but what we really did is proving the parallel repetition theorem for a specific family of games. This is a follow-up work of our previous one on all three-player games with binary alphabet, and the setups are basically the same. I will talk about the basics of parallel repetition for self-containment, but if you're familiar with it or have followed our previous work, you are free to skip the first 5 or 10 minutes and head straight to the new stuffs. Let's start with the basic definitions. What is a three-player game, or more generally, multiplayer or prover games? Well, the game consists of a verifier or referee and k provers or players. The players cannot communicate with each other and could only interact with the verifier. Initially, the verifier samples a question or input, which consists of k parts from a fixed distribution Q, and it sends to player I the ith part of the input. Each player then, based on the part of the input it receives, generates an answer and sends it back to the verifier. The verifier decides whether the players win with a fixed predicate over the inputs and the collection of the outputs. Since each player only sees his own part of the input, their strategies can be seen as k functions from an input alphabet x to an output alphabet y. The game value is defined as the maximum winning probability, where the maximum is taken over the strategies and the probability is over the randomness of the inputs. The players could have randomness themselves, even shared randomness, but for the discussion of the game value, without loss of generality, we could always assume that their strategies are deterministic. In the n-fold parallel repetition, the verifier now samples n inputs independently from the same distribution Q and send to player I the collection of part I in each one of the inputs. Now each player can decide its n answers based on the n inputs it receives altogether and send it back to the verifier. Now the players win if they win all n copies of the game. And their strategies can be formalized as k functions, each from the direct product of n input alphabets to the direct product of n output alphabets. These strategy functions, not necessarily, but could be chosen to be just the direct product of the optimal strategies in each individual copy. Therefore, the value of the n-fold parallel repetition is always at least the original game value to the nth power. So a natural question is the reverse also true, so that the value of the parallel repetition always equals to the power of the original game value? Bornau has given a negative answer to this question, and then Feige actually gave a game such that when repeated twice, its value does not change. This shows that the n-fold parallel repetition value can be exponentially larger than the original game value to the nth power. So Feige and Lovász resorted to conjecturing that for every game, as long as its value is less than 1, its parallel repetition value should go down at least polynomially fast. This conjecture was proved for all two-player games in a famous work by Raz and then improved by Hollenstein, and proved for a class of games called connected games by Dinner, Harsha-Vinkan, and Yun. But besides these two cases, until very recently, for every other game, it was only known that the parallel repetition value goes down to 0 and goes to infinity. This bound proof by Verbitsky is basically inverse Ackermann. What we showed in our previous work, combined with the missing piece that we proved in this work, gives the following statement. For every non-trivial three-player game with binary input alphabet, the parallel repetition value goes down at least polynomially fast. Before we talk about the proof, let's briefly mention the applications of parallel repetition. For two-player games, the most prominent application for the parallel repetition theorem is the gap amplification in PCP theorems and hardness of approximation. It was also used to amplify the gaps between quantum and classical models. The parallel repetition for some specific game has a surprising application over a geometric object called foams. And the proof of the parallel repetition theorems can be used and modified to prove direct sum and direct product theorems for communication complexity. For multiplayer games, less application was known as the conjecture was not known to be true yet. But recently, Mittal and Raz showed that if we can prove a strong parallel repetition theorem for multiplayer games, we could have some good lower bounds for non-uniform Turing machines and circuits. And also, if we can prove parallel repetition theorems for multiplayer games, we might also be able to get direct sum and direct product theorems for multi-party communication complexity. So the first thing I want to talk about in our proof is a lemma by Feige and Verbitsky, which we call the distribution changing lemma. It roughly states that proving parallel repetition for a game reduced to proving it for another game with nothing changed but the distribution being a subdistribution of the original one. This turns out to be a very powerful tool, and later we will come up to it again, but for now, we only use it so that we can focus ourselves on the uniform distribution, because every distribution has a part of it being a uniform distribution over its support. And now that we fixed the distribution to be uniform over some support, we can actually do a case analysis over all possible supports for 3-player games with binary input. Those are just subsets on the Boolean cube. And on the Boolean cube, we have several symmetries that help simplify the classification. There's a symmetry over the 3 players, and for each player, there's a symmetry between the 0 and 1 inputs. And as it turns out, there are exactly 6 cases. The first 2 cases are covered by the exponential bounds that is already known, and 3 out of 4 remaining cases were proved in our previous work with polynomial bounds. The last case, which we call 3-point support, was left open in the previous work. There, we only managed to prove parallel repetition bounds when the output alphabet is also restricted to be binary. Although in that case, we do get a exponential bound for the 3-point support. So in this work, we complete the missing piece by proving a polynomial bound for all games with this 3-point support without restrictions on the output alphabet. And the proof of it will be the rest of this talk. So here is our main claim. For every game with this 3-point support, there is one player gets 1 and the other 2 players gets 0. The parallel repetition value goes down at least polynomially fast. What we did here is something completely new. We find a family of games that are the hardest among all games with this support, and they have a very simple description. For every integer k, the game gk works as follows. The input is uniform over this 3-point support. The output of the first 2 players are binary strings of length k, and the third player outputs a number between 1 and k served as an index pointing towards the first 2 players' outputs. And here's the winning condition. If the third player receives 0, its output should point at a 0 in the binary string outputted by the other player who receives 0. And if the first 2 players receive 0, their outputs should be bitwise OR to an all-1 string. That is, at every position, at least one of them outputs an 1. So here's an example to help you understand this definition. Let's say the third player's output is 5 when it receives 0. So the 5th bit in the first player's output when it receives 0 should be 0 in order to win. The same happens to the second player. The 5th bit in the output of the second player also needs to be 0. But that just means the bitwise OR cannot be an all-1 string. So they cannot win all the time, and the game value turns out to be 2/3. Notice that in this winning predicate, the output of the player who gets 1 as the input does not matter at all. This is not a coincidence, and we can always assume that because the player who gets 1 knows the entire input and should always act optimally. Now we say this family GK is the hardest in the sense of reduction, just like what happened in Cook-Levin theorem in complexity theory. Our reduction theorem states that for every game G with the uniform 3-point input and output alphabets of size k, its parallel repetition value is bounded by the one of GK. Therefore, proving parallel repetition theorem for GK implies parallel repetition theorem for all games with this support. And the reduction turns out to be very nice and simple. We just translate the outputs of the first two players via these two translation functions. The first one, for example, you can think of it as we write out the winning matrix of the first and third player in G, where the rows are possible outputs of the first player and the columns are possible outputs of the third player. We put a 0 if the two outputs win on input 0, 1, 0, because the output of the second player does not matter in this case. And the translation function simply translates each output of the first player to its corresponding row. We claim that every winning instance in the original game G, the translated output wins on the same input in GK. The claim can be verified literally by definition. The only thing to notice is that the two translated outputs for the first player and the second player cannot share a 0 at the same position, because otherwise it implies a strategy for G that always wins, and it contradicts to the fact that G has value smaller than 1. For parallel repetition, we just apply the translation to each copy of the game and we get our reduction. All right, so the problem now is actually to prove parallel repetition bounds for these hardest games, GK. And to start with, we want to do something similar to what we did in our previous work for the specific game called with this 3-point support called the anti-correlation game. And the idea is called global strategies. First of all, let's fix the player strategies to be the optimal ones. And generally speaking, a player admits a global strategy when its output follows some fixed pattern that is independent of its input. So here for the game GK, since player 1 and 2 don't want to output a 0 at a common position, let's just say they only output 0 in two fixed sets of positions that are disjoint. These two sets are their global strategies. And if such sets really exists, it is not hard to prove that the winning probability is exponentially small, because the third player, whenever it receives 0, has to correctly guess in each copy which player is playing with to point at a 0 in their outputs. And that just happens with very small probability. But that requirement is too strong, so we consider some relaxations. Let's actually define the sets to be the positions where the player outputs 0 with non-negligible probability over its input. Non-negligible means larger than some threshold p. Outside these sets, the player can still output 0. It just happens with negligible probability. And these two sets does not need to be always disjoint. Let's just say they are disjoint in the first half of the games, we can still bound the winning probability to be exponentially small. And it will now get plus with an error term p, right? And why do we think this kind of relaxed global strategy exists? And why would these two sets, as we define, be disjoint? The intuition, as we said, is that if they intersect, they just lose. So let's assume that player 1 and 2 has some common position to output 0 with probability p. Since they don't have much information about the input of the other player, they should have some kind of independence and simultaneously output 0 with non-negligible probability. And this statement here is not exactly true, but we will see how to fix that. But anyway, this just means that there shouldn't be many such positions if they want good winning probability. It turns out that if we choose P to be into the epsilon for some small constant epsilon, we can remove all copies of the game where there exist such positions by fixing. And that will still leaves us with most of the copies unfixed, and we get our desired bound on winning probability. So now let's execute the above intuitions rigorously. Suppose we have a position at repetition I and index j, where with probability p, the inputs and outputs for player 1 and 2 are all 0. We want to force it not happening by fixing the inputs and probably also some outputs on this repetition. So we look at the decision tree and pick an alternative outcome. The input on this copy has 3 cases, and 2 of which are good for us already. But if 001 happens, we then have to look at the output of the player 1 at this position. And if the output is 1, we're also good. And if it is 0, then we look at the second player's output. And if it is 1, it's still good. And the only bad case, which is the red leaf here, is when the second player also outputs 0. And that happens with probability at least p. So now we try to fix the outcome to be some green leaf. Because going into the red leaf we fail, the green leaf must compensate for the winning probability. So the law of total probability implies that there must be a green leaf with significant probability, which also increases the winning probability by a non-negligible amount. And since the winning probability cannot exceed 1, so using it as a potential function, we can argue that this fixing process must stop after a few number of steps. So what we just did there is to fix some inputs in some repetitions, and we just roll these repetitions away. But we also probably fix some outputs of player 1 and 2. And that exerts some limitations on their remaining inputs separately. So these limitations can be reflected as product events E1 and E2 on player 1 and 2's input. They do not have very small probability because we only pick large green leaves, as we said, and we repeat it not too many times. But more importantly, conditioning on these product event, on every position remaining, player 1 and 2 does not simultaneously output 0. We want to take a step ahead and say that it is nearly independent for the 2 players, meaning that it's either player 1 almost always not outputting 0, or player 2 almost always not outputting 0. If we manage to show this, we can split the unfixed positions into 2 disjoint sets, and we are basically done because of the reason that I talked about earlier. And to prove this near independence, we did it via Fourier analysis. Let's think of all possible inputs to player 1 as an n-dimensional Boolean hypercube, and the event E1 as a subset of it. Some of the inputs in E1 make player 1 output 0 at that fixed position, and we mark them with dark blue color. We use a function a to describe this situation. It is non-zero only on E1, and it is 1 if player 1 outputs 0 and -1 otherwise. Now if we fix player 2's input to be some binary string y, then the input x of player 1 that is compatible with y needs to have disjoint ones with y. So they are on a sub-hypercube defined by y. And on each coordinate where y is 0, x has half and half probability to be 0 and 1. So it's actually uniformly distributed over the subhypercube. This makes it really easy to examine the expected value of function a and the absolute value of function a. These two values are interesting because the expectation of function a reflects the probability that E1 happens and player 1 also outputs 0, while the expectation of the absolute value of a is just the probability of E1. So what we really want to prove is basically saying that the ratio of these two values are nearly independent of the choice of y. Now, if we look at the Fourier domain, these two values have very nice representations. For example, the expectation of function a given y is just the sum of the Fourier coefficients of a under y. Well, this expression is clearly not independent of y as we wanted, but if we look at the large subset of y, the weight will be concentrated at the lower levels. And if it is really concentrated and concentrate all at the level 0, then it's basically independent of the subset y. So we derive the following inequality that bounds the difference of our target value and the 0 Fourier coefficient of the function a. Let's take a closer look at this. The part of the Fourier coefficients can be bounded by grouping them according to the Hamming weight of U and use level k inequality. It is exponentially large in the Hamming weight, but fortunately, the last term is exponentially small in the Hamming weight. Recalling that our distribution on the 3-point support, this term is clearly just 1/3 to the power of Hamming weight of U. However, it is still not small enough. And even if you look at Hamming weight 1, it gives us a problem. So the saving grace is the distribution changing lemma. We just change the distribution so that the second player gets 1 with really small probability, keeping the other two cases half and half. Then the last term cancels out the bound by the level k inequality and even leaves us with something polynomially small. And now we only need to deal with the first term. And what we are going to plug in here for the set of y are two things. The event E2, and within E2, the event of the player 2 outputting 0. The latter one is fine since if it has small probability, that's already what we want and we are basically done. So we are left with the task of bounding the probability of E2 itself. Remember that we had a bound for E2, and that is exponentially small, which is not good enough for us. So we want to be more careful when we do the fixing steps. Notice that E2 only changes if we pick the blue leaf here. So instead of the winning probability, the actual potential function that we consider is this thing here that has two parts of winning probability and one part of E2 in it. The law of total probability now becomes an inequality because of Jensen's inequality, and the direction is exactly what we wanted. And bounding this potential function actually gives us lower bound on the winning probability and E2 simultaneously. Also with the perk that if we actually choose the blue leaf, which means that the rest of the green leaves are just too small to be chosen, the potential function still increases by a non-negligible amount. So our previous argument still works, and E2 is now guaranteed to have polynomially large probability. And putting all the pieces together, there goes the core of our entire proof. All right, so let's talk about some future directions. The obvious thing to do is to prove parallel repetition for more games using or extending our new methods, and meanwhile find applications for these new parallel repetition bounds. The question that interests me the most is to find a family of games that is the hardest over all games. We can syntactically find such games for every input support and the output alphabet size, but those games are just very hard to prove bounds for. If we want to show some natural family to be the hardest, we probably need some non-black box reduction instead of the nice black box one that we did here. And finally, I want to know if our new method have any impact on things like density Hales duet or other closely related combinatoric problems. And that's the end of my talk. Thank you.